Okay, here we are back for the next part of this series, and I'm trying to jump back and forth between the less entertaining, or if you want to say more boring material, which you need to learn. I mean, you need to understand the stuff that you can't see. When you look at a flashlight and you flip the switch, you can see the position the switch is in. You can see whether or not light's coming out of the lens, right? You can see if the bulb's on or off. But that's it. That's all you can see. When I see a flashlight, I see much more than that. I see all the metal conductors inside. I see the chemical reaction taking place in the batteries, the electrons flowing through the metal strips, and the filament heating up. Now, we primarily did incandescent bulb flashlights because that's more traditional. Very few people have flashlights anymore that have those little incandescent bulbs. Mostly they're LEDs. The only difference between the LED flashlight and the incandescent is that there is a polarity consideration for LEDs. Now, sometimes they trick you. They put in two LEDs, so no matter which way the batteries are, one of them lights up. We're not going to do that. Let's look at our flashlight circuits and talk about LEDs, incandescent, battery, series, parallel, currents, volts, etc. In this episode, we're going to continue on with our basic electricity with Grandpa. And we're going back to Tinkercad, and we're going to stick to real simple circuits. If you cannot explain these real simple circuits to other people, then you don't understand electricity. So you need to get to the point where you understand it well enough that you can explain it to someone else. And that is kind of a criteria in the training industry. If you really want to understand something yourself, try explaining it to another person that doesn't already know all about it. So here we have a flashlight. And for the sake of contemporary, I have two flashlights. Both of them take a single AA cell. And I want you to notice that normally in a flashlight, the battery slides in the back of the flashlight, and the smaller end, which is the positive, makes contact with the back side of the bulb. And then when you screw the cap on the end of the sleeve of the screwdriver, it makes contact with the end marked with a minus sign. And then that goes through the body of the flashlight through a slide switch to turn the flashlight on and off. So I have here AA battery. I have an incandescent light bulb. That's the old-fashioned style that actually generates heat. It lights up a filament. So you can see in the bulb here, that's the filament. It's a piece of tungsten wire that gets hot because electricity is going through it, and it becomes white hot. And the reason it doesn't just burn out is because it's enclosed in a glass bulb that has been evacuated, which means they've removed all of the atmosphere, all the oxygen, all the air that they could. Otherwise, the filament would just burn out. So if I start the simulation here, and you see if I go down here to the switch, I click the switch on, you see the incandescent bulb comes on. Now over here, I have an LED flashlight. And when you see when I flip it on, off, on, if you look here, it's supposed to be white. But that's a limitation of this Tinkercad software application. So that's what you're looking for, as it to go light gray from dark gray. So you see both of them operate great. Now notice that the text on the battery is upside down. And that's because I wanted the plus end of the battery facing against the bulb, not the negative end. But I can scroll down and do the exact same thing. But in this case, I've also flipped the battery around. Notice here, we've got minus and plus, and here we've got plus and minus. So in other words, this is a single battery flashlight, both an incandescent on the left and a LED on the right. Now there's some parts here that you may not recognize, but it takes this resistor right here is what limits the current flow through this LED so it doesn't burn out. but you don't see this when you have an LED flashlight. So what I did was I flipped the battery around to show that it doesn't matter which way you put the battery in with an incandescent flashlight as long as the contacts make contact. Now, they won't in most flashlights. If you try to put the battery in backwards, it won't make contact like it's supposed to. But let's turn this one on, and you see that for both of these incandescent flashlights, whether the battery's in one way or the other electrically, not mechanically, but electrically, the bulbs light up. So now we'll turn on this one. You see it went light gray, but watch, this one does nothing because the battery's in backwards. That's because this is a light emitting diode, and this has to go to the positive terminal, and that has to go to the negative terminal. It is polarity sensitive. Incandescent is not polarity sensitive. It doesn't care what direction you run current flow through it. The little wire inside of here is going to get hot and light up. Let's take a look at some other circuits. Okay, here we have a flashlight that has two batteries. So we're still in the simulation. Now, I could click on stop simulation and it stops. Click on start and it starts. So we turn on the single battery bulb, and now I'm going to turn on with two batteries. Now, you may not be able to see clearly, and I'll see if I can zoom in here a little bit, but this bulb is brighter than this bulb. So two batteries in series, connected end to end, plus minus to the bulb, give you a brighter light than just one battery. So two batteries in series give you more light than one battery. Okay, now let's go down a little bit further here. Now what I've done is I've reversed, see with the incandescent here, it didn't matter which way you put the battery in electrically, either one would light the light bulb. See, they're both lit, and the batteries are opposite of each other. Now, if we go down here to the incandescent with two batteries, you see it's brighter. If we go down a little bit further, now you see I've reversed the batteries. So now it's not plus minus, it's minus plus minus, or plus minus plus. Either way, the two batteries, they're in backwards. One of them is in backwards. Now with incandescent, if they were both in the other way, like we did up here, remember up here we had, you could put the battery in either direction electrically and it would work the same. Now down here, if you put one of them in backwards, I'll turn it on, you see it does not light up. That's because you've got one battery pushing electrons out this way and the other one pushing electrons out this way, and they oppose and cancel. So if we go down a little bit further here, and I'm going to use a meter, and I will reduce this in size just a little bit to get it all on the screen. So here I have a voltmeter that is across the battery. Here I have a voltmeter across two batteries that are opposing. Now see, I can stop the simulation here, start it back up, measuring, so you know what a meter looks like. As a matter of fact, we'll just pull aside here a little bit. This is what the meter would look like. You see it's got two leads on it, a black and a red, and it doesn't matter where it's set right now, but this knob right here allows you to pick all of these different ranges for voltage, current, and resistance. This is a multimeter, or some people call it a DVM, digital voltmeter. We're using it here as a voltmeter. So in the Tinkercad software, it allows you to attach a voltmeter to your circuit. So I threw the voltmeter right across. So I've got the black lead here, which is negative, going to negative, and the red lead here, which is positive, going to positive. I get 1.5 volts. If I put it across two batteries, but they're opposing each other, they cancel and you get 0 volts. Right below it, now we have two batteries that are not opposing. See, This one's minus plus and then plus minus. This one's minus plus minus plus. So you get 3 volts. Now another kind of meter is an amp meter that measures current. In order to use an amp meter, you have to insert it into the current flow. So when we turn this on, we get current that goes from the electrons flow out of the battery, through the filament in the bulb, heat it up, go through the switch, go through the meter, and then back to the positive side of the source. So a voltmeter, you put it across the pressure or the voltage, but an amp meter has to be in series. That'd be like if you were going to do a water flow meter on your garden hose, you would have to mount the flow meter in between the spigot, the faucet, the valve, the knob, and the end of the hose. And then as the water goes through the flow meter to go out the end of the hose, as it goes through the flow meter tells you what kind of flow you're getting. So amp meters have to be mounted in series. Voltmeters are placed across. Now, here we have another circuit, and this one is a series circuit. It's got 3 batteries. So now if we turn this on, I don't know if you can really tell, but this is brighter than this one, okay? And if we put meters on this one, we would see that we had basically 4.5 volts, and we would have about 90 milliamps. That is, we'd have more voltage, more current, which means more light. Now, that's series with batteries. Let's say we put 2 batteries in parallel, okay? So I'm going to pause this, rearrange my circuits, and then I'll be back. Instead, I decided that I'm going to modify this circuit while you watch. Blow it up here a little bit. To do that, to add the amp meter, I'm going to have to remove this wire, and then I could go here to get my meter, go down here and grab a meter and drag it in here, and I'm going to drag it over here, and I'm going to put it right there, and then I'm going to take and I'm going to add a copper wire from here over to here, and from here over to here. Now, if you don't like the way these things kind of line up, you can adjust them until they suit you. Okay, now there I've added an amp meter. So I'm going to go ahead and start the simulation, and you see, it's a voltmeter. I forgot to change it to an amp meter. So I'm going to stop the simulation. I'm going to select it. I have to go up here and say that item is a amperage, not voltage. My bad. Start simulation. Now with 1 battery, I would get about 30 milliamps. So you see, 1 battery, 30, 2 batteries, 60, 3 batteries, 90. You get the drift. As you start increasing the voltage, you proportionally get more current. In other words, if you double the voltage, you double the current. Okay, now I'm going to stop the simulation. I'm going to go get another meter and put it in here. And I'm going to put the meter leads across the batteries. If I'm not real fussy about how the thing looks, I'll just leave it like that, and I'll start the simulation. So I'm going to turn off both switches, okay? So notice, with 2 batteries, 1.5 volt, 1.5 volt, in series, voltage adds to get 3 volts. 1.5, 1.5, 1.5, add together is 4.5. Because the switch is off, there is no current flow. Now notice what happens to the battery voltage when I turn on the circuit. You see it dropped a couple hundredths of a volt. That's because if you measure the voltage on a battery with no load, in other words, you're not drawing any current, doing any work, you get the full battery voltage measured. But if you put a load on it, in other words, if you start using it, you don't really get 3 volts out of 2 1.5 volt batteries. Just like down here, you've got 4.5 volts until you flip the switch on, and now you've got 4.36. So this should give you a pretty good jump on voltages added in series or added in parallel. Now the next step would be to go down and put two of them in parallel. So up here, still 3 volts. I'm series. These two are in series, you get 3 volts. We go down here, you got 2 batteries, but you've only got 1.49 volts at 31.1 milliamps. That's because they're in parallel. When you put batteries in parallel, the voltage does not it does not change. So it doesn't matter how many batteries you put in parallel, the voltage is going to stay the same for the circuit. You just now have, you could say, a larger battery that will light up the bulb for a longer period of time. It has more amperage capacity, but the voltage does not increase. So I'm going to pause and make some changes. So now you see I added a bunch of batteries in parallel. So all 2, 4, 6, 7, it could be any number. It could be 100 of them in parallel. Okay. This circuit and this circuit are somewhat identical, except this has more batteries in parallel. So I'm going to turn on this one, start simulation, turn it on. We have 1.49 volts and we have 31.1 milliamps. That's how much current is being drawn. Now I'm going to turn on the next one and you'll see just a slight change. Look, you got slightly more current and slightly more voltage. The reason is because each of these batteries has resistance internally. In other words, between the two terminals of the battery, there is resistance to current flow. Remember, the electrons are flowing from minus to plus, minus to plus, minus to plus. And when you got two of them in parallel, then these two both are sending out electrons through the bulb back to both of the positive terminals. But the voltage, it's 1.49, and you look over here, it's 1.5 because there's less total resistance in this larger bank of batteries, so you get slightly higher current and slightly higher voltage. You wouldn't be able to tell the difference in the bulb as far as the brightness goes. The advantage of this circuit is if you leave both of these on, now if these were flashlights, and I don't think I've ever seen a flashlight that has this many batteries in parallel. It may look like it when you slide them in there, but they're not. So if you turn them both on and just let them sit there, this one over here, these two batteries would go dead long before this even started getting dim. So the more batteries you have, the longer the light is lit because it takes longer to discharge the batteries. Now remember that these batteries, or this cell, this AA cell, 1.5 volt, remember it has two dissimilar materials, carbon rod and a zinc shell, and then it has a chemical paste in there. That chemical paste, as soon as it's assembled, starts a chemical reaction that causes electrons to build up on the negative terminal and a deficiency of electrons on the positive. But if you start discharging the battery, using it, once it uses up all the chemical reaction of that paste, the battery's dead and you throw it away. These are not rechargeable batteries. And now we're going to jump onto something else. Okay, that's good enough for now for DC circuits, battery circuits. And in the next episode, we're going to get more into electromagnetic induction. That means how you generate electricity with a generator or an alternator. Because the whole world doesn't run on batteries. It mostly runs on alternating current, AC. So what comes into your house, into your business, out on the power lines, that's all AC, alternating current, which means it's going back and forth 120 times a second. It's going that way and then that way 120 times a second. It's called 60 hertz. So one complete cycle, 60 times a second, this way and that way. So in the next episode, we're going to get more into electromagnetic induction and fields. Thank you.